Hey, AP Physics C, this is Horner, and we're going to go through circular motion. We're going to go through just the first couple of sections. One of the things that I would do along with this is I would read sections 4.5 and 4.6 in your online book. So if you go into Mastering Physics, you'll find those. So this is circular motion. It goes round and round. Part one talks about just regular uniform circular motion. Uniform circular motion basically just shows that if you have a particle moving at a constant speed, similar to this one, around a circle, here's our radius r, the velocity vector is always tangent to the circle. So if we know what the velocity is tangent to the circle, we're looking at that constant speed. The period is the time it takes for that particle to go all the way around for one revolution. The distance for a circle is called the circumference, and that's basically just 2 pi r. And the speed around a circle then is the distance, which is 2 pi r, divided by the period, which is t. So that's just some basics that we needed to cover so that we kind of know what they are. For the very first example problem, it says you have a 4 centimeter diameter crankshaft. It's turning at 2,400, and RPM stands for revolutions per minute. So if you look down here at the bottom, you'll see it says 2,400 REV over 1 minute. That's that revolutions per minute. We're going to convert that revolutions per minute to revolutions per second, since we do most things in seconds, and we end up with 40 revolutions per second. If the crankshaft turns 40 times in 1 second, the time for one revolution would be 0.025 seconds. So all we did here is we said the period is equal to the inverse of this thing here, which is really the frequency. So now we know how long it takes for one revolution. And the speed of a point on the surface where the radius is 2 centimeters, which is really 0.02 meters, is now just the velocity, which is equal to 2 pi r over the period. And so here we have 2 pi times our radius, which was 0.02, divided by 0.025 seconds. And so that gives us 5 meters per second. And that is the answer that we have. Obviously, that this speed is the tangential speed. For the next thing, we're going to talk about angular position. So now we don't have XY coordinates anymore. Instead, we're talking about the position of a particle, looking at its distance from the center. So if we say this is the center of circular motion, here's our particle, we have our distance r. And we also talk about our angle from the positive axis. So here's our angle. If we go counterclockwise, so if we go in this direction, then we say that it's positive. If we go the other way, if we start here and come around, then we say that that is negative. And so you want to get used to that. If you think about it, that's kind of the way it works in trigonometry, is we always start at the x and then we come up and go around this way. And that would be our counterclockwise, and that is positive. The next part is the measure of an angle. So we can use the arc length. The arc length basically is just this distance that you see here, s, and we can use that arc length s that the particle travels through on the edge of a circle with a radius r, and we know that the angle in radians, so we're going to use radians now, and that's approximately equal to s divided by r. So if we go back up, here's our s and our r. If we know both of those values, we can divide the two, and that will give us our angle. If we know one revolution is 360 degrees, that's equal to 2 pi radians. We know that on a circle, 1/2 of the way around is pi radians. So all the way around would be 2 pi radians. And so here 1 radian is approximately equal to 57.3, well, exactly 57.3 degrees. So it's pretty close to 60 degrees. It's really important here that you see the displacement along the curve is equal to the radius times the angle in radians. So if I want to know this displacement s, so if I look at the arc length, that's equal to the radius, which is what we have here, times the angle, and that angle has to be in radians. So if I want s, it's just r times the angle in radians. For angular velocity, this is approximately the change in the angle divided by the change in time. So if I start at this position and I go to this position, I know that my average angular velocity is going to be the change in the angle. So there's the change in the angle divided by how long it takes to get there. So as the time interval becomes really, really small, our time interval gets closer and closer to zero. We can think about the definition of instantaneous angular velocity. So just like the derivative of position versus time is instantaneous velocity in a linear sense, we can do the same thing with angular velocity. So we've got this little symbol down here. This is called omega. I like to call it butt because it does. It looks like a butt. If you were standing behind somebody and they were sitting down, that would be their butt. So anyway, that is angular velocity. And as the time approaches zero, our change in the angle over change in time is going to be our angular velocity. Okay, so just a little bit of pre-calculus for you there. The SI unit is a radian per second. So when we talk about butt, which is angular velocity, we know that if it's going in a clockwise fashion, so we start here and come around, that will be positive. And if we start here and go around clockwise, that would be negative velocity. So that's the difference. Just be really careful with that. On a number line, we know left is negative, right is positive. So for this, if we go up and to the left, we have positive velocity in terms of angular velocity, and down to the right is negative angular velocity. We're used to velocity as the slope of the position versus time graph. We can do the same thing for circular motion, but the angular velocity is now equal to the angle versus the time graph at a particular time. We're also used to this equation in order to find velocity. And so we could say final position is equal to original plus velocity times time. Notice this is the same equation, but now we are using circular motion. So our final angle in radians is equal to our original angle in radians plus the angular velocity times time. Um, this is, we call it butt, and this is alpha, so I call it fish. They are related to each other. If you go fishing, you do sit on your butt. So you're going to learn a little bit more about angular acceleration later. Let's go on. If we look at this problem, it says figure 4.29 shows the angular position of a painted dot on the edge of a rotating wheel. Describe the wheel's motion and draw a velocity, angular velocity versus time graph. If I start here and move up, you'll notice that I'm getting further and further out in terms of the number of rotations, and then it backs off and comes back. So this is the angular position of the wheel over time. They want us to figure out what is the angular velocity versus time. So from 0 to 3 seconds, I need to find the slope. Just like we would find the slope of a position versus time for linear, we're going to do angular position, which is radians, versus time. So at this point, we're just going to take 6 pi, which is our final, minus 0, so that's 6 pi radians, divided by 3 seconds is our time change, and that's 2 pi radians per second. From 3 to 5 seconds, you'll notice that now we have an angular velocity. And so we have, we go from 6 pi down to 4 pi. So 4 pi minus 6 pi will give us negative 2 pi radians divided by 2 seconds, and that's negative pi radians per second. And then anything past that has a slope of just 0 because there's no slope here at all. Now that we've done that, we're able to make our graph. So the first speed that we have, or velocity, angular velocity, is 2 pi. So we do that for exactly that 3 seconds. And then we come down and we want negative pi for 3 to 5. And then anything greater than 5, there is no angular velocity. And so we've plotted that. So you want to do this on your note sheet too. Angular velocity and period. As a particle goes around in a circle one time, its angular displacement, which is the change in the angle, is equal to 2 pi times 2 pi radians, and it's during that time interval, which is the period. So here we can see that the absolute value is equal to 2 pi radians over the period, or the period is equal to 2 pi radians over the absolute value of the angular velocity. The period alone only gives the absolute value, and that's because our period can't be negative. You need to know the direction in order to do that. So remember, we said counterclockwise is positive and clockwise is negative. Here's a good example. A small steel roulette wheel rolls counterclockwise. So right off the bat, we know that that is positive. Inside a 30 centimeter diameter roulette wheel, the ball completes 2 revolutions in 1.2 seconds. So they want us to figure out what is the angular velocity. If it's 2 revolutions in 1.2 seconds, we know it takes about 0.6 seconds for 1 revolution, so that's our period. And we take 2 pi times 2 pi radians divided by 0.6, and that gives us 10.47 radians per second. That's the angular velocity. They want to know what is the position at 2 seconds. So we're going to assume that our original position is 0. It starts at 0 radians. After 2 seconds, its position now has changed. So we've got our 10.47 radians per second. That's our angular velocity times 2 seconds plus 0 gives us 20.94. Now we're going to say that 20.94 radians is really 3.33 times 2 pi. So 3 times 2 pi radians plus 0.333 times 2 pi radians. So here really we've got 3 times 2 pi radians plus 2.09 radians. In other words, it's completed 3 of our revolutions and is 2.09 radians, which is 120 degrees, into its 4th revolution. So 3 revolutions, that's what this means, plus here we're this far into the 4th revolution. So you would basically just say its final position here in radians is, final position is about 120 degrees. For part 2, this is section 4.6 in your book. This is velocity in uniform circular motion. So velocity vector for a particle moving in a circle only has its tangential component. So we said that here's its tangential component. Vt is really the change in that arc length divided by the change in time, which through which that particle moves around the circle. And remember, we did say s is the arc length here. If I take the derivative of s, which is arc length, is equal to the radius times the angle, we end up with this equation. So we can say that the tangential velocity is equal to the angular velocity times the radius. So anytime I want a linear thing, I just take the angular thing and multiply it times radius. That's really the big key here. Tangential velocity is positive counterclockwise motion and negative for clockwise motion. So same thing that we've been doing. If I have a particle moving clockwise at 2 meters per second in a circle of radius 40 centimeters, it has an angular velocity. So here I'm going to take negative 2 meters per second because it's moving clockwise. It's negative. We're going to divide it by 0.4 meters. That's our radius. So we get an angular velocity, that's our butt, of negative 5 radians per second. Vt and the angular velocity are negative because the motion is clockwise. So notice here that the meters cross off and we end up with a dimensionless unit, and we're going to put in radians there, and that is dimensionless. The acceleration in uniform circular motion for a particle, if it's moving in a circle, remember the acceleration, the linear acceleration, always points toward the center of a circle. So if I'm swirling something over my head, that angular the tangent, the acceleration is pointing towards me. So V and A are always perpendicular. You'll see that on the circle itself. Now what we're going to do is we're going to look, and we see that the change in velocity, okay, points towards the center of the circle. So that is the acceleration, that centripetal acceleration is always towards the center. If I want to find the magnitude, we can see from an isosceles triangle and the velocity vectors as these keep getting, if you look at the change in velocity, you'll notice it's right here for these two velocities at these two positions. Okay, we can now just say it's the velocity times the change in that angle. So that's basically what we're looking at here. we're looking at the change in velocity, so that's dv, is equal to the velocity times the d times the angle itself. If I use this equation and I say for uniform circular motion at constant speed, the velocity is equal to the arc length divided by time. That's the radius times the change in the angle divided by time, change in time. And so to rotate through one angle, I have this equation. If I combine the two equations, my acceleration in a circle is equal to v squared over r. So you've seen this equation before. If I want if I want the acceleration, that's just the angular velocity squared times the radius. So there's another equation where we're just multiplying by the radius in order to get this centripetal acceleration. This is not angular acceleration, okay? This is centripetal. This points towards the center of the circle. So if I have a Ferris wheel, it has a radius of 9 meters, and it rotates 4 times per minute, they want to know what is the magnitude of the acceleration that the riders experience. So here we've got 2 pi r, 2 times pi times 9 meter radius, divided by that 15 seconds, we get 3.77 meters per second. So that's our tangential velocity. I'm going to take that, square it, divide it by r, and that gives us our centripetal acceleration. So it's 1.6 meters per second squared. And that is the end of the video notes.